Okay.
Okay, so welcome everybody to HAO Colloquium today. Our speaker is Elizabeth Redak. Elizabeth is a PhD student at the University of Michigan in the Climate and Space Sciences and Engineering Department, working with Drs. Enrico Landi and Chip Manchester on studying CME plasma evolution. She graduated from the University of Maryland with high honors in physics and astronomy in May 2021. Her primary research interest is connecting what is observed by remote sensing to what is measured in situ. Elizabeth is also starting to look for postdoc opportunities. Today, she will be speaking on understanding the evolution of CME plasmas in the solar corona from EUV spectroscopy and charge state composition. Elizabeth.
So first of all, thank you for inviting me. I'm really excited to present my PhD work, and hopefully everyone can hear me okay. So yeah, let's just jump into it. So first, this is just what I'm going to be discussing, give a background, some introduction, discuss the observation that I will be focusing on, what simulation I use for this, the results, and some summarizing points from everything. So starting extremely simply, what is a coronal mass ejection, or a CME? And to me, they are eruptions of magnetized multithermal plasma from the solar corona, which you can see in this really nice image from LASCO, a nice CME going. And here you can really clearly see the three-part structure. So traditionally, CMEs are thought to have a three-part structure. Obviously, some people debate this, but for the purposes of this discussion, I'm going to keep with the three-part CME. So we have very clearly our fast front out in front, which is our CME propagating into our coronal material. We have our dark cavity that contains more of the flux rope structure. And then finally, we have the bright core that contains our cold, dense prominence material following behind. So there are many ways of observing CMEs. Obviously we see here a white light image, so this would be a remote sensing. There's also EUV spectroscopy, full disk, EUV narrowband imagers, and then we can go all the way out to 1AU or wherever we have in situ satellites such as ACE, Solar Orbiter, Parker Solar Probe that can all observe CME plasmas. So one of the things I do is, I study CMEs with EUV spectra. So why do we want to do that? So it really gives some of the most rigorous constraints to different plasma diagnostics, everything from electron density, electron and ion temperatures, ion abundance, plasma motions, non-thermal motions. There's a lot that you can get into it. And especially with spectroscopy, we have single slit often, or rastering. So we can get really close to the solar surface in ways that other methods can't always get that resolution. So for instance, EUV narrowband imagers, we can see the full, beginning of the CME and as it continues to evolve, but it can't do as rigorous of plasma diagnostics as, the spectral lines can do. You can get differential emission measures, but you can't always, really constrain a lot of the plasma diagnostics. And with white light imagers, we see a lot of what happens as the CME continues to evolve outwards, but it blocks out the inner corona where there's a lot of acceleration occurring and a lot of structure beginning to form. So all of these things would be great, to use when looking at CMEs. But, I really think that UV spectra in particular can provide a lot of information. So as we can start moving out, away from very close to the sun. And we can start seeing how CMEs are observed in situ. So obviously you can observe CMEs with temperature, velocity, magnetic field, but I'm really going to be focusing on charge states. And so this is an image from the Lepri and Rivera 2021 paper. And these three middle panels, and you can't see my cursor, so that's nice. You can see the carbon, oxygen, and iron charge state distributions as relative abundances, I believe. And generally it's been found that about 95% of CMEs contain hot plasma material, which means we have higher ionization charge states of iron. So, we'll see, I think on average, higher than about iron charge state of 12 or 13, but we really do see a lot of iron 16 material, which you can start seeing up here. It's also been shown that a lot of these CMEs have something called a bimodal distribution or a two-peak distribution around iron 10, which you can see the CME is actually these red lines I didn't mention. But you can see, we have maybe something that's, average of iron 10, and then we have this iron 16 creating that bimodal distribution. But you can see that there's this other part in the CME in particular, which has really low charge states in all of the different elements. And this would be our prominence material. And only about 6% of CMEs observed at 1AU with ACE contain this cool prominence material. And then often it has adjacent material mixed in, as you can see here in the carbon and the oxygen and also the iron. So, that leads to a lot of questions. And this about why this is happening and such. So one point that's really important to this discussion of charge states, I believe, is the evolution of charge states in these CME plasmas. So as charge states evolve from low in the solar corona, eventually the density decreases as we get further away from the sun, and the charge state composition stops evolving and freezes into the plasma. In solar wind, we've seen with the Michigan ionization code from Landy et al., this is the 2012 papers, that the charge states tend to freeze in between 2 and 5 solar radii. As you can see here, we have distance, and then, our iron charge states seem to freeze in. This is the ratio from the freeze-in location at about, 2.5 solar radii. That's great. But when we actually look at CME plasmas, they really can continue to evolve well past that 2 to 5 solar radii location. So this is from the Rivera et al. 2019 paper that also used the Michigan ionization code and followed multiple different plasma components in the CME. So we have the densest plasmas, from our prominence, as well as just other components of our prominence corona transition region type PCTR plasmas. So here in the top plot, we have our iron charge states for 1 to 7 plus. And you can see that, and these would be mostly related to our prominence plasma. You can see by 15 solar radii, very few of them have frozen in at all. And then when we go into more of our PCTR plasmas, you see that these iron 12 through 16 plus ions might have frozen in around 9 solar radii. So really, we're not getting this freeze-in in the same places as in the solar wind. And I actually talked to Craig DeForest about this earlier. Are they even freezing in at all? So, that's another area that we want to discuss. So kind of the overarching theme of my work is how we can connect these different types of observations from the low solar corona as we go out. Observations by UVCS, so other EUV spectra, has shown that 70% of CMEs do contain prominence material. But measurements at ACE only show that prominence material makes it to 1AU about 6% of the time. So why does that happen? Obviously, people have looked into this. The Lee and Raymond 2012 paper said that the covering factor or the filling factor meant that not a lot of that material makes it to 1AU, and if it does, the chances of a satellite observing it is pretty low. So, but there's also potentially other processes between, the sun and 1AU or wherever we have the observations that will potentially cause, heating, cooling, movement of the CME plasma. So that's something we want to look more at. So in my opinion, this really highlights our need to connect different types of observations of CME plasmas. And this is, I think, a very hot button topic at the moment. A lot of people have been, doing this connectivity work to track in situ measurements back to source regions. We have ballistic bat mapping, which the Yardley et al. 2023 paper showed with Solar Orbiter. We have these in situ observations of slow solar wind, and they went back to nearby an active region to see the upflowing regions, as well as models. We can propagate backwards and forwards from the solar corona with models like WSA or other global MHD models to really see what these source regions are. So this leads to my work. So as was said in the introduction, as you're probably starting to guess, my main kind of goal is to connect remote sensing observations with in situ measurements in different CME plasmas. And I'm going to be using 3D magnetohydrodynamics or MHD models. And this leads to a few questions that I'm trying to answer. So the first is, how does non-equilibrium ionization EUV emission evolve in the CME's evolution? And that kind of leads to, what would observatories, moving away from EUV, but maybe towards visible, that UCOMP COSMO would measure. As well as, how do the charge states evolve to these freeze-in locations? And, this would affect the EUV emission. And then how does the CME's energetics, the heating budget, really affect the charge state evolution? So this is everything I'm going to attempt to talk about in the rest of the presentation. So that brings us to the observation, which is the cartwheel CME. And so this was a CME event that erupted on April 9, 2008 at 9:30 from an off-limb active region. You can see, actually, this is an XRT image of the CME plasma evolving outwards. And it's called the cartwheel CME, actually, because it had a very strong southward deflection, which caused the plasma material to rotate. And I think Sabrina Savage made this quite some time ago. This is considered to be a traditional three-part CME. So this goes back to what I was saying very early on, that, for the sake of this discussion, the three-part CME is a great discussion of the structure. This event was not observed by any in situ observations. We only have remote sensing observations, but we have really nice remote sensing observations. So we have XRT, of course, but I'm actually going to be focusing on the Hinode EUV imaging spectrometer, or Hinode ICE observation. And you can actually see the isolate superimposed on the image here. It was observed in a sit and stare configuration over its entire wavelength range and pointed at 1.1 solar radii, so very close to the solar surface. The CME itself entered the field of view at 9:30 and left the field of view after 10 o'clock. So the observations were taken with a 10-minute exposure in the sit and stare, which allowed us to capture 4 sets of spectra containing CME material. And in particular, it captured the bright core that contained prominence material. So that's really nice. We can do very detailed plasma diagnostics with this, especially because this is the only CME that was observed with the full range of ice spectral lines. So this really allows us to really constrain the plasma diagnostics in CMEs in ways that, many we haven't been able to do with ice previously. So I mentioned the way that I'm doing this is using MHD modeling. So I use the Alphane Wave Solar Atmosphere model, or AWESOME, which was developed at the University of Michigan and is within the space weather modeling framework. And it's an extended MHD model that includes physical turbulence terms, or parallel and anti-parallel turbulence. It has reflection that can give us the turbulence cascade, partitioning of the turbulence dissipation into heating of different species. In particular, that allows us to get 1, 2, or 3 different temperatures in the model. So that would be proton and electron, or parallel and perpendicular proton electron temperatures. We can get the wave pressure gradient to accelerate the solar wind, collisional and collisionless electron heat conduction, and radiative plasma cooling using the Chianti values. So all of that being said, has lots of really great physics, and this has been really well validated through multiple papers during solar maximum, solar minimum, as well as for different Parker Solar Probe approaches. And the boundary conditions we use is the synoptic solar magnetograms to drive everything. And as a note, AWESOME is included in Forward, so if you're interested, please check that out. Judith Zent spent a lot of time putting it in, so it's really great. So a few more words about my simulation. So I include additional refinement over the active region to increase the resolution to be 3 arc seconds as viewed from Earth. And that is to prevent, magnetic diffusion of the flux rope. But also, this is the spatial resolution of ice, or very close to it. So we are able to get up to the resolution of ice, in the simulation domain, which is great. As well, we're using the Gibson-Low flux rope because it has been shown to reproduce the 3-part structure really nicely and awesome. And as I said, this is a 3-part CME, so it's great that we are able to reproduce that. And then, most importantly, we're calculating the EUV spectra observation. We're using very similar as observed spectral the observation orientation. And we're including the non-equilibrium ionization charge states and solving those self-consistently throughout the simulation domain. And I have a few more words on that point in particular. So we follow the time-dependent charge state evolution equation to solve the equation self-consistently throughout the simulation domain. So as our event continues to expand and evolve, the charge state evolution equation is doing the same thing at the same time. And within this, we include radiative and dielectronic recombination, collisional ionization, excitation and autoionization, and photoexcitation to do that. And then using these, charge states, we can also calculate the non-equilibrium ion fraction in the contribution function to actually synthesize our EUV spectra for comparison to observations. And this is particularly important because when we actually see what the differences are, so here is the ratio of our non-equilibrium to equilibrium ionization contribution functions for multiple ice spectral lines. So here we have iron 8, the 185, iron 9, the 171, the iron 10, 174, and the iron 11, 182.29 lines. You can see that there are multiple differences in the coronal holes in most of them, as well as near the streamer belt that we have going on. So that's really emphasizing that there are a lot of differences, and then especially in CMEs that are so dynamic and changing so much that it should be really important to include non-equilibrium ionization charge states. So with all that being said, we can start moving on to more of the results. So here is the CME evolution in the low solar corona during the first 2 hours of the eruption. So the electron density and temperature, and hopefully it's coming across a little bit less grainy than what it's showing on here on the screen. But we see the flux rope, evolving out nicely, and we see this denser material and colder material kind of being pushed downwards and creating this like hook shape, which will come back as it goes. And so we're really seeing that deflection that we, observed in the CME material, as well as the start of a rotation occurring. We see the dense material for the prominence, the cavity with the lower density. So all of that looks pretty nice. So from that, we were like, okay, let's see how it looks with the iron charge states. So here's just a snapshot because I wanted to point a few things out. So this is a snapshot at 30 minutes post-eruption of 4 different ions. Oh, I can hide this. Oh, perfect. Okay. And so we have the iron 2+, 6+, 11+, and 16+ charge states. And you can see the 2+ is our coldest, would be coming from our coldest prominence material, our densest material. So that is our prominence material. Very nice. We see that southward deflection that I was just discussing, as well as that hooking for the cartwheeling effect. Our iron 6+ is more of our transition region temperatures, and we see it very clearly enveloping the prominence with very high spatial resolution, which is nice to see. In our more of our corona line, so in our 11+, we see that the corona is really being moved out by the prominence. We don't see them being too co-spatial. We also see that the streamer that was just above the active region really got opened up by the CME. And in the flux rope, we're starting to see, maybe a little bit more coronal material. And then really in the flux rope, we see a lot of iron 16+ in comparison to elsewhere. So that's really emphasizing the heating in the flux rope. So all of this generally looks like what we would expect to happen. So we then could, begin answering our first set of science questions, which is, how does this EUV emission evolve as the CME propagates, and, how would actually the visible also look? So here is first, this is a lot of information, but we have the iron 8, 185, and the oxygen 6, 183, and 184 lines. The left side is our observation, and the right side is the simulation. And you can see the observation is evolving so much because we only have it at 10-minute exposures. But in this simulation, we can save this at any number of exposures we want. So saving it every minute we see, it's very dynamic. A lot is happening as the CME passes, but there are a few general trends I would like to point out. First, the line intensity evolution, the actual intensity values aren't the same, but the evolution is very similar. We see, the highest intensity in these transition region and colder lines, at about 30 minutes post-eruption in the observation, but around 26, 27 minutes post-eruption in the simulation, which do correspond to the same times between the observation and the simulation. We also see blue shift in the observation for the iron 8 and oxygen 6 lines, but the simulation isn't showing us much blue shift, so I have to look at that slightly more. So, but we also see, and one of the things I'd like to emphasize is that, the simulation data at a 1 minute time cadence shows much more evolution occurring than our 10-minute exposures, as is expected. So it's really important to include higher temporal resolution data so that way we don't just like average over some very dynamic structures we may have. So yeah. Then I can also synthesize some UCOMP or Cosmo, potential Cosmo observations. So here is the iron 15 706 nanometer line. This is just 2 minutes post-eruption, so not too much has really happened at all. So, in the intensity, we might say we're seeing some interaction of the flux rope with the corona, and we see maybe some broadening of our spectral lines. But we also do start to see that blue shift occurring in, the center of the flux rope. So, okay, this looks fine. And as a note, this is also all with non-equilibrium ionization. When we actually go to 34 minutes post-eruption, we see a lot has already passed. Some of these structures are unphysical. I'm still working on the fitting routines. I put these together quite recently. But in the actual full width half max right here, we see some structure in the flux rope material, an increase in the full width half max, then a decrease and an increase again, which is actually occurring from the fitting. So that's really interesting to me. And then we see this really large redshifted plasma behind this flux rope front that's, starting to leave this field of view out in front. So all of this is really interesting to just, very simply see for myself. But to really, drive the fact home that we need non-equilibrium ionization when we synthesize these things, here's the equilibrium ionization solution and the non-equilibrium ionization solution. Again, ignoring some of these structures right here. When we actually take the ratio of the two, we see a significant number of differences where the flux rope is expanding. So we see more enhanced intensity in this iron 15 line, and then in the non-equilibrium ionization version than in the equilibrium version. So again, this continues for me to emphasize, non-equilibrium ionization is really important when we're synthesizing these EUV spectral lines and, preparing for, observations by future observatories like Cosmo. So moving from, these images or these specific lines, we can start looking at spectral diagnostics. So here is, so I began with the differential emission measure, or which describes the distribution of temperature in our plasma along the line of sight. That's how I like thinking about it. And here's just the observation. I want to show this first. So we have temperature on the x-axis and DEM on the y-axis. And the solid lines are our DEM values. And this blue line is our pre-event corona. And then each of the colored lines is one time of these CME's passage. And you can very clearly see we have two plasma components. We have our coronal component peaking at about 6.1, which you can very clearly see our pre-event corona matches nicely. And then we have a second peak, which we are interpreting as our prominence material, peaking at much lower temperatures. I think it's about 5.3, 5.25 temperature. And this second peak is only occurring when the CME passes. Even after, these four spectra, I'm not showing the post eruption material here, but we don't see this material anymore. We also see that both the prominence and the coronal material decrease in the DEM as the CME passes, because it goes from this green line to the purple to the red and then to this yellow-orange color. And, we interpret that, there are a few ways we can say this. The first can be, oh, we just see less material in the slit. The CME is expanding outwards. There's just less stuff, which definitely makes sense. Or we can say that the prominence is heating very close to the sun. And that's something, we can definitely look a lot more at with simulations, which I'll actually discuss this much later on towards the end of the talk. But as well as we see in the corona, it decreases, and that's because this prominence is pushing out some of this chroma material. So that all makes sense. So when we actually superimpose the simulation results, we can see, our pre-event corona looks pretty nice. And we definitely see some similarities and differences between the observation and the simulation. The prominence material is definitely enhanced similarly to the observations and decreases in the DEM value with time, just like we saw before. The exact structure is not the same, but we're pretty happy with it. And then when the CME is passing, the coronal material gets pushed out quite a bit more in comparison to observations. And we're really thinking that's due to the structure of the prominence material being unrealistic. Placing it just at the bottom of the flex rope might not, give the most realistic version and push out too much of the coronal material. But I talked to Sarah about this, and maybe it's the topology. So we're going to try different things out now. But all of this being said, we're actually not too worried about that because the thermodynamics look nice. And I will be showing this in the next few slides. So we can do comparisons with electron temperature from these spectral lines. So on the x-axis, we have the effective temperature, which is our DEM weighted temperature. And we're using this as the proxy for where the spectral line or where the ions form. And on the y-axis, we actually have the temperature from temperature-dependent line ratios. And here is just the observation. And from the observation, we can actually only get out iron temperatures for comparison, which is fine. So we have, the iron 8 to represent the transition region, and then iron 10 and 11 to represent our coronal lines. And these look fine. So when we superimpose the simulation, which is the triangles, we see first a variation in the effective temperature due to differences in the DEM. So, I just discussed this, so that's fine. But the individual, line ratios compare within uncertainties for the most part. So that means that the thermodynamics driving these iron spectral lines and the temperatures that form them is being represented well in the transition region and in the corona. Even if the coronal material is being pushed out slightly more, the temperatures still look good. So we can continue with the electron density. And again, we have effective temperature on the x-axis and density from density-dependent lines on the y-axis. And now we can get multiple different plasmas. So we have our coronal material from, our higher ionization irons and silicons and stuff. Then we have our transition region material at intermediate temperatures and, slightly lower densities. And then finally, we have our oxygen 4s and 5s, which we're using as our prominence material lines that are cold and dense. So again, looking at the simulations, they're the triangles. We see that variation in the effective temperature due to differences in the DEM, but the individual line ratios compare well. So in all of these different plasmas and in multiple plasmas, the thermodynamics are being captured correctly. So that's really nice to see. So throughout it. So yeah. So that kind of answers and addresses my first set of science questions. Obviously, there's a lot more that can be done, but I'm open to suggestions. But moving a little bit further away from the sun to, the freeze-in of the charge states and how the energetics continue to those points, we can move on to the second half of everything. So the first question we can very simply ask is, what do the charge state distributions look like when frozen in? So I actually made this slide originally for AGU, and I was like, oh, it looks like at about 5 solar radii, just like in the simulation while I was making videos, the charge state material doesn't really seem to be changing much. So I took an average over this material that contained the prominence, made a carbon, oxygen, sulfur, and iron charge state distribution. I said, hey, those look pretty good. We see, our prominence material, especially with those iron 2, 3, and 4 plus materials, as well as in most of the other elements, we have those low ionization values. And then, we see our oxygen 6 plus really being enhanced, which we expect from in situ observations of the solar wind. And we see our iron 16 plus also being enhanced, which is, very indicative of a CME passing at 1 AU. So I was like, this all looks great. So how does this compare to observations? Well, I mentioned this event doesn't have any in situ observations, but we can compare it to similar observations from other CMEs. So this is an observation of that filament prominence material from a completely unrelated event, but it does have the filament material, and it's from January 9, 2005. And you can very clearly see we have those iron 2, 3, and 4 plus, just like in the observation, as well as that peak for the iron 16 plus material for, the hotter parts of the flux rope. So I was like, this all looks great. And then we said, okay, so why don't we actually track what happens until we get to this location? So we began using Lagrangian plasma parcel tracking through the heliosphere. And I'm tracking 22 different plasma parcels. I'm not showing all 22 of them. I'm only showing 4. So I'm showing one that's from the middle of our prominence material, this is a temperature distribution of our flux rope right before we erupt it. So we see the prominence material right at the bottom. And so we're taking a plasma parcel from the center of it, then part from the flux rope where we have very high twist, part from the cavity, and then one from the corona, like right outside the flux rope material. And we followed these 4 just for this presentation, but we followed many more from in and around all of this material. And here's actually what it looks like when the plasma parcels are trying to freeze in. So this is every 10 seconds, we save the location and the data of what's happening. And the blue is our prominence, the red is the flux rope, the green is the cavity, and the purple is the corona. And you can see that all of the plasmas are traveling at different speeds. So we see that they're all, at different locations, even at the same time. And you can already start to see, as we start getting out to 2, 3 solar radii, especially for the flux rope, cavity, and corona, they appear to not be evolving so much, but there is some continued evolution, even if it's kind of hit, the flux rope is going to be at the highest charge states. The cavity is going to be slightly higher than the corona. But the prominence is really what begins heating, and you can start seeing it right now, starting to poke up in the back here at about 2 solar radii. And we continue to see that even much past 5 solar radii, it's still evolving quite a bit. So generally, we need to spend more time freezing this in. But this is kind of a long video, so I also made this into individual line plots. So here is radial distance on the x-axis, and this is 1 or RS -1, so it's above the surface of the sun. And we have average iron charge state, iron 2 plus, 6 plus, 11 plus, and 16 plus relative abundances. And the colors changed slightly, so the prominence is now in black. The flux rope is in that red color, the blue is the cavity, and the purple is the corona. And you can see further out in the solar corona, up until 10 solar radii, we're still seeing evolution in multiple different plasmas. We see it in the flux rope, we see it in the corona, and the cavity is not even, or the prominence isn't even close to that point yet. So we're definitely seeing evolution pretty far out. We see that only the prominence contains these lowest charge state values, as is expected for the most part. But you see a huge drop off at 1 solar radii past the solar surface, so 2 solar radii. And that's because we're starting to see a lot of heating occurring. And we see, increases in the relative abundance of iron 6 plus, 11 plus, 16 plus. So, what's really happening here? Well, we need to look into it, that's for sure. And then we also are starting to see some cooling in the flux-rope material, as well as in the corona. We see increases in the relative abundance of that iron 6+ material as we continue to get further out in the corona, which I think is actually pretty interesting. But these are all just like individual charge states. So we can actually see what the local plasma looks like. And hopefully in the room, this is all big enough to see, but we have that same radial distance on the x-axis. And then here we have density, temperature, velocity, and magnetic field. And we have gravitational potential energy, electron thermal energy, kinetic energy, and magnetic field energy, all average per particle. And all the colors are the same as before. And so we see that decrease in density as we expect as the CME continues to go out and, we're approaching freeze-in locations. We also see as we're continuing to go out into the solar corona and expand, most of the plasmas, such as the flux rope cavity corona, are decreasing in temperature and in electron thermal energy, as is more or less expected for something expanding and adiabatically cooling. But we see this huge peak at that one solar radii location in the prominence material. Something's happening that's causing it to increase in temperature pretty rapidly, which is directly evident in that charge state material I was just talking about. So we're still trying to look at what exactly is happening here. Is it reconnection driving it or something else? But it's something that's very interesting. And then also going back to what I was showing with the DEM way earlier on, we see that in the prominence material here, we see a lot of heating occurring and a lot of evolution in the electron thermal energy happening close to the sun, where we saw that decrease in that prominence material. So maybe that's a hint as to what, might be causing heating very close to the sun. But again, that's something we still need to look a little bit more at. So yeah. So that's the last of my, results. So now I'm going to summarize a few of the things I was attempting to show. So the first is that, the EUV spectral diagnostics of this event compare well to observations of multiple plasmas, both with the EUV spectra, and overall maybe more realistic structures, different initiation mechanisms, looking at different topologies of even the Gibson low flux rope will, allow us to get even better results, even if our thermodynamics look great at the moment. It's also something that I really want to drive home is that non-equilibrium ionization effects are really important to consider in CMEs above, as it's continuing to evolve, because so much is happening in such, short amount of time that we really need to make sure that we are considering those correctly. Overall, the charge state part also compares well to previous unrelated observations. And using simulations, as I discussed very early on, we can really directly see where the heating, cooling, and all of these different things are occurring to the time of freeze-in and potentially see where and if it freezes in at all. And then finally, as I was just saying, 3D MHD models provide some of the best opportunity, in my opinion, to understand how CME plasma evolves from remote sensing to in situ measurements, and really allows us to predict what future observatories we'll see, like Cosmo. So that's all I have at the moment. If anybody, we obviously can discuss more now, but also if people have other questions, here's my email. So
Thank you. So questions from the room or from virtual participants, you can just unmute and ask questions.
Got one. So the prominence it's heating up as it's going when it's down below, you're saying. So is it then becoming part of the coronal core that surrounds it? Is that where the plasma is going? And because you were talking about how you could see that it was not co-spatial. So do you look at the evolution of that structure and if there's, and can you see that kind of feeding of the coronal part?
Yeah, you definitely can. I don't have any of the, I probably can find some animations if you give me like some time, but I've made so many videos of this, but you really can see generally you know, very early in the evolution, you don't see them being co-spatial together. You see, you know, very clear distinction between, you know, you have the prominence, you have that kind of like transition region material, you see the no coronal, very little coronal material, and you have the flexor elsewhere. But as it continues to go outwards, it does tend to like feed in. You see like lowering amounts of, you know, that iron 2+ with the increasing amounts of iron 10+ and all of that. So you can see it start to mix slightly. And I probably can find some animations of this somewhere and send it to you. So yeah.
I'm wondering if with Cosmo, if you could observe that transfer of plasma from the cooler prominence lines to the coronal lines.
You know, I haven't really thought about, I don't know how low down in the corona or how high you'd actually start to see that. That's something I'll definitely look at though, and let you know to see, you know, maybe, you know, for some of the cooler lines, if, when they'll start heating significantly.
At what heights and exactly. Okay.
Yeah,
Cool.
I can look at
Interesting.
So you talked a lot about, sorry, man.
that. Yeah, thanks.
You talked a lot about ionization fractions and DEMs. And it made me think about just how geeky you want to get about forward modeling. You know, these things are passing out through the middle corona and the transition from collisional excitation to resonant scattering. I don't think you've necessarily captured that in your movies, right? Which are mostly physical quantities.
Yeah.
Thought about trying to compare to some of these newer middle coronal imagers people are developing.
So I haven't actually thought about doing that. I've definitely like, you know, created white light images to compare for LASCO, but you know, I definitely could talk to other people at Michigan about this and like seeing, you know, what, especially for some of the more energetic events, what will we see in the middle, what would Punch see, you know, as we get out further. That's definitely something that's very important.
Punch, of course, I care about, but I'm also thinking about
any of these middle corona type projects, definitely. I haven't done any of that personally at the moment.
On your, can you show your results from your simulation and the model that you were comparing them side by side? Yeah, you can just this one's fine. So you from here it looks like your prominence kind of died at one solar radii.
Yeah.
And so we assume all that material is converted now into coronal temperature because the iron.
Yeah, I mean, it definitely seems like it's really getting converted into the other material.
You think that's typical because this is a weird CME? Because I don't know, do we expect to see prominence still intact at past one solar radii? Or
Yeah, I mean, and there has been observations of this prominence material for this a number of CMEs. It's, you know, I think Lebrine Rivera said it was about 6%. That's not a huge number. I forgot the exact number that corresponded to, and I don't actually remember much about those individual CMEs, why they made it all the way out there. But, you know, this is kind of the point I was trying to say. It's like, you know, does everything just get heated away? And what exactly is the heating mechanisms of this? And that's kind of what I'm trying to figure out and stuff. And
because the other stuff that's like is getting more heated, like other than just the filament prominent stuff, the other stuff is not getting
it's not getting
energized additionally.
Yeah.
So I guess like if I'm imagining like it maybe some additional turbulence or something is causing the heating, then you would think the other stuff, will be also being heated also at that point, but you don't really see that other stuff going heating more.
No, it's definitely something I'm still looking a bit more at, but it's definitely
Okay,
we'll see, for sure.
Mm-hmm. John?
Yeah, I was going to say a long time ago, the SMM chronograph was primarily white light, but had an H alpha filter, and it did observe prominences out to even 5 and 6 solar radii in H alpha. And so also these prominent structures they do take up less volume. So it's not surprising that for reasons that they're heating up and they just take up a smaller volume, that they're not as well observed in situ. It could be telling us something about, you know, are they sitting on field lines that are beginning to come maybe a little more disconnected? Because then you can have plasma sitting on a field line, it's not getting heated, where the cooler material is going to live longer. So I think you have a lot of interesting results here
Yeah.
that with more modeling and considering where's the reconnection happening and which field lines may be
Yeah.
becoming, disconnected would be interesting.
I completely agree.
Yeah, just to follow up on that, as we were talking about, I think most of the implementations and awesome of the Gibson Low is essentially it's a shared arcade. It doesn't have the topology of it may have the Fluxar row topology or the tethered Fluxar, but not the Sphermac. And when you start getting into the tethered Sphermac topology, what is characterized by are in the purely analytic form, which is going to be different when you do your numerical implementation, but nevertheless is portions of that structure are detached.
Mhm.
And so it'd be really interesting to look at the difference in the way the thermodynamics play out on those the partly attached versus the completely detached field lines within the structure. That would be cool.
Yeah, no, I mean, I completely agree. We need to know exactly what field lines are doing what and where everything is going, where the heating is going, and and seeing different initiation mechanisms or different versions of these initiation mechanisms, what is happening. And so I will look into the code you're going to send and stuff to really see what that is starting to look at. So.
Any other questions from online or from the room?
So when is your freeze-in? Do you find your freeze-in threshold in this data?
Not yet. I'll say that. I would, we could arguably say maybe the flux rope, but it's like starting to cool some. So we're still waiting. I am continuing this part of the simulation like as we speak, basically. And maybe at Shine I'll be able to say this is where it freezes in, but we'll see. So or it doesn't freeze in if it just ends up leaving the solar corona and we don't see anything. So
Any other questions from online?
thank you.
We can talk later, but oh, sorry, go ahead. No, I mean, we could keep going talking, but so I didn't, so this is a really cool model because it's non-equilibrium ionization is so hard to figure out for. So, do people use this for other, like active regions or?
There have been just like full global simulations, like the ones I showed from Judith Zent, who has done this for many different spectral lines that are often observed. But we haven't applied this to active regions. I think there's going to be, soon a lot of work using this from our group at Michigan and stuff. That includes this in CMEs and just very
Those flare loops would be very awesome.
Yes, post-flare loops would be very awesome. I was talking to Craig before actually about this earlier. So, yeah.
And let's thank our speaker today for a very nice talk.
Cookie.